Okay, I'll get things underway then. So, folks, welcome to the June 4th meeting at the Ottawa Centre of the RASC. A special welcome to our visitors and those visiting from the other RASC centres. And special welcome to our visiting guest speaker, Dr. Josh Speagle. So on to the next slide. Welcome Rick Wagner from Elgin. I just drove by there the other day, down to Kingston yesterday. Okay, security alert. We are on Zoom, and we are in Zoom webinar, which is more secure than some of the other Zoom services. However, some people may try to put a web URL in the chat box or the Q&A box. Please do not click on those. If you have a question for any of the speakers, please type it into the Q&A box. We're not going to be monitoring the chat box. And what I will do is I will read out the question to the speaker so that they can answer it, and we can capture that in the recording. Next slide. There we go. So here's what we have on for tonight. I've got the Ottawa skies for June. We're very pleased to have Dr. Josh Speagle talking about mapping the Milky Way. We have a 5-minute break with the Messier and Moon Challenge. We have Paul Klauninger talking about the June 10 partial solar eclipse coming up. We have our observations and announcements. So we'll just move ahead then. Members in the news. So belated congratulations to Andrea and her Sky News photo of the week from February the 12th. So congratulations, Andrea. Okay. So the Ottawa skies for June. Just a second here. So move on to the next slide. Take a look at the moon phases. So full moon is on June the 24th. We've got our longest day of the year on the 21st. And this full moon was known by the early Native American tribes as the strawberry moon because it signaled the time of year to gather ripening fruit. It also coincides with the peak of the strawberry harvesting season. This moon has also been known as the rose moon and the honey moon. This is the last of the 3 supermoons for 2021, and the moon will be near its closest approach to the Earth. It may look slightly larger and brighter than usual. Next slide. So we do have a comet. This is Comet 15P Finley. This one has a short period of about 6.4 years. Not particularly bright, but this is where it's going to be across the skies for June through August. Paul is going to go into a lot more detail about this, but we have the annular solar eclipse coming up on June the 10th. It's going to be very near the horizon. It's 3.2 degrees off the horizon at maximum eclipse, so you got to have a good view of the eastern horizon. 5:40 in the morning on Thursday. So far, the weather's looking promising. So you have to be an early riser to catch this. Next slide, please. Solar eclipse safety. Paul's going to cover a lot of this off in his talk, but absolutely never, ever, ever stare directly at the sun and wear proper goggles to look at it. So I'm going to let Paul cover that off in his speech. I don't want to steal from that. So move on to the next one. Again, similar thing. So safe solar observing, very, very important. All this will be up on our website, and it will also be in our Astro notes as well. So sun, the days are getting getting longer and longer. And as you can see, the sunrise is basically the same between the start and the end of the month. But by the end of the month, we got a slightly longer day, longest day being obviously June the 21st. Mercury is not really visible until July the 4th. The reason I'm bringing up July stuff is that July 4th occurs before our next meeting. So we have the greatest western elongation for Mercury. So you look for the planet low in the eastern sky just before sunrise on July the 4th. Venus is visible in the evening. And Mars is visible in the evening as well. Jupiter is visible before sunrise, but it's starting to move into the evening skies. By the end of the month, it's rising at 11:30. Saturn, visible late evening and through the night. So by the end of the month, 10:41, it'll be rising. Uranus is visible before sunrise, and as is Neptune for this month. And the next one is our cartoon of the month, set up for the meteor shower. You can see they're obviously looking the wrong way. That never happens, does it? Okay, moving on then. So I continue to offer a virtual introduction to astronomy. It's a 45-minute program for Beavers and Sparks, 1-hour program for all other groups. I've done a lot of outreach to scouts and guides, but I also do it for adults as well. I will actually be doing one of each of these sessions, the 45 and the 1-hour one, both in July and August for the Ottawa Public Library, and I'll post that to our distribution list. And then on the next slide, I have a follow-up to the one for the older group called Astronomy, the next presentation. And I'll be doing one of those in July and one of those in August for the Ottawa Public Library as well. So I will send you out the links to the Zoom calls for that. So I'm very pleased to have Dr. Josh Speagle come to speak to us. He's a Banting Dunlop postdoctoral fellow, jointly hosted between the Department of Statistical Sciences, the Department of Astronomy and Astrophysics, and the Dunlop Institute with the University of Toronto. So welcome, Dr. Speagle. And Chris is going to stop his screen sharing and allow you to move ahead with yours.
Great.
So Chris, stop sharing there. Okay, just hang on a second here. I'm going to highlight you as well. Just give me a second here. Okay, so Chris, let me see where we're at here. Chris is having some challenges here. Oops. A few options. So, there we go. Okay, we're all set. A few little technical glitches. That never happens. Okay, Josh, there we go.
All right. So, did everyone see this okay?
Mm-hmm. That looks great.
Perfect. So, yeah, I mean, thanks so much for both the invitation and the great introduction. So it's super cool to be here today and to speak to such a cool audience. So as Dave already mentioned, I'm Josh Speagle. So I'm a Banting and Dunlop postdoctoral fellow at U of T. And so I'll be talking about some of the work that me and my collaborators are trying to do to try and map out the Milky Way, sort of in the modern astronomical era. And I'll sort of get into what I mean by all of this and sort of why I think it's like a really cool thing to do, to try and map out the night sky and do sort of like this, cosmic cartography. So one thing that I think is always good to start is to ask, what is the Milky Way? And I think for this group in particular, the answer is often pretty obvious for like a bunch of, observers and astronomers, right? It's the thing that you can see when you go outside with the telescope that cuts across the sky. This is an enduring image. This is one taken in particular from ESO, one of these large telescopes in Chile. But you can see this in, across all different cultures, societies, and through time, right? People always describe sort of, this band of stars that cuts across the night sky. And that's also where it gets its name from sort of the Greeks as well. And this is like one way to define it observationally. But really, the Milky Way, as referred to today, is what we call the galaxy that we live in. And so really, almost all the stars that we see on the night sky, including sort of the dark band towards the center of the galaxy, is part of the Milky Way. The best view that we can get of this today is an image that looks like this, which is taken from the Gaia space satellite from ESA. And this is just showing essentially a 360-degree view of the Milky Way, kind of projected onto 2D. And of course, you see some interlopers. This is Andromeda, our nearest neighbor. And but in general, you can, lots of this stuff that we see here, all these stars are really part of the galaxy, and all the black areas are really also dust and other features of the galaxy as well. The thing that's difficult, right, is that we're inside the Milky Way. And so this means if we want to know what it looks like, it's a lot like trying to map something from the inside out, trying to understand the human body if you're inside of it the whole time, or for instance, trying to understand what you look like personally if you don't have access to a mirror. And by just trying to look at, one of the best ways that you could try and do that is to just ask other people, right? What do I look like? Or maybe I look like this person that's nearby. And that's a lot of how we understand and contextualize our galaxies, by going out and looking at other galaxies that we can see from the outside and look down on them and say, what do these look like? Maybe this is what the Milky Way looks like. So these are just a snapshot of, some of the hundreds of millions and billions of galaxies that we can observe today that we think look something kind of like the Milky Way. They have this spiral structure, the blue regions indicating regions of active star formation. You can see dust, you can see features in the center like these bars. You can see that when you look at them edge on, you can see features that are similar to what we see in our own galaxy. So maybe this is kind of what we're looking through, but they come in like a variety of shapes and sizes. And so this isn't obviously perfect. We want to be able to understand our own galaxy as well, not just by looking at other ones. One of the pictures that often is shown in the press when talking about the Milky Way is something like this. And unfortunately, this isn't really what the Milky Way looks like. This is an artist's conception, but it's based on real data. And I'll actually show you what that data looks like a little later in this talk. So you can compare sort of how much we're extrapolating today. But one of the things that I really want to do in my research is to make a picture like this a reality, where we can actually say, this is what we really think the galaxy looks like. And we've constructed it using data from hundreds of millions and billions of stars to actually make something like this, not just an artist's conception, but a real picture that we can show people and say, this is actually our galaxy. Of course, in this regime, we are more or less here. So in this picture, we think our sun kind of is in the outskirts along one of these arms, kind of living a little bit out from the center and kind of looking in. And so that's why when we look at the Milky Way, when we're looking through sort of all this dust and gas in the center, that's sort of why we see some of the images that we do. So what I focus on is trying to understand, how do we go from sort of the pictures that we see on the night sky to a 3D model or a more complicated model of the Milky Way that we actually want to reconstruct to understand sort of our own position in the galaxy. This is important for a couple reasons. I think hopefully everyone agrees this is really cool. I think it's super cool. But it's also important for sort of three main reasons. The first is trying to understand our origins. Understanding what the Milky Way looks like today can tell us a lot about how we got here, how the Milky Way formed, grew, and assembled in mass over time, and also give us a little bit of clues in our place in the universe. It is important to know, is the Milky Way kind of like a typical galaxy, or are we kind of in a bit of a special place? Maybe that means that our own origins might be a little different than we thought. The second is, on the same token, and with regards to the search for extraterrestrial life, a lot of what's required to map out the galaxy really means that we have to understand stars, and we have to understand dust. And understanding these things like our sun is a crucial ingredient for understanding how life formed and the environments that other planets are exposed to, which is important for understanding sort of habitability in lots of other planets around other stars. And finally, this is interesting from a fundamental physics perspective as well, trying to understand galactic structure and dynamics, how stars move and how galaxies evolve, can help provide clues to unanswered questions like the nature of dark matter. In fact, this is how dark matter was in some ways originally discovered, was by looking at the movements and motions of stars in the Milky Way as well as other galaxies. That was the first hint that something was amiss in sort of physics that was led to the discovery of dark matter. So in this sort of presentation, I'll give a bit of a background on what exactly is the history of trying to do this work and what are the concepts that are important to understanding how to go about doing this. I'll then talk very briefly, but mostly skip over part 2, which is kind of the math involved with trying to infer stellar properties. But I'll leave that to something where I'm happy to go back to it if there are lots of questions. In part 3, also some of the recent results that me and my collaborators have done trying to map out the local solar neighborhood, which included some unexpected discoveries about the sort of nature of the local arm that we think our own sun lives in. And finally, some initial steps we're taking towards mapping the galaxy at large, trying to use 100 million stars to really visualize and understand what the galaxy looks like in some amount of detail. So in terms of history, one thing to start off is that trying to map out our own galaxy actually has a history that goes back about 250 years. In fact, the first map of the Milky Way that we can find was constructed by William Herschel in about 1781 and was published in sort of 1785. And that's shown here on the right. And what Herschel did is he has the sun positioned at the center. And his map of the Milky Way has some features that are in common with the map that we know today. And in particular, you'll notice that there are a lot fewer sort of stars sort of going up and down. It's a lot thinner and seems to be flatter, sort of looking like what we think our galaxy looks like, which is a little bit like a disk. You'll also notice that it's asymmetric. It's not the same sort of on one side versus the other. In particular, you'll notice this cutout in the center here that seems to correspond to some of those dark spots that you see when you look at the actual Milky Way. And so building on this over the last 250 years has required a lot of work and sort of tireless scientific advancement by many, many astronomers to understand how do we go from sort of this initial map by William Herschel, which gets a lot of big things right, to what we sort of understand about our galaxy today and what we think it looks like. So how did Herschel do it? You know, how did he actually go about making a map of the galaxy way back in time like this? Well, essentially his idea was just to go out and count stars. If you go on the night sky and you just see where are the stars located, and he made two main assumptions to start to make this transition from 2D to 3D. The first was that all stars have the same intrinsic brightness. In other words, when you see a star that's fainter, that's because it's actually further away. One way to think about this is that the observed brightness is actually the intrinsic brightness divided by the distance squared. This is known as the inverse square law. So if stars are fainter, that just means they're further away. Like, for example, if you see a light bulb from further away, it does look fainter compared to one that's right in your face. The other is that there's no real material between us and other stars. That just means that if you don't see stars in a particular region, that's because there aren't stars in that region. So in other words, the density of stars that we observe is a good tracer of the true underlying density of stars that exists in the Milky Way. It turns out, unfortunately, that both of these assumptions aren't true. And in fact, Herschel was involved in helping to disprove, especially the second assumption. But it took a while to get there. And I'll deal with each of these in turn. The first is that not all stars turn out to have the same intrinsic brightness. And in fact, in around 1910, work by two scientists, Hertzsprung and Russell, really helped to show this very clearly, that when you look at a bunch of stars and you generate a plot essentially of their brightness, their true intrinsic brightness, as well as their observed color. So bluer stars are kind of on the left here and redder stars are on the right. That what you find is that stars follow a sequence, or they seem to have a pattern, but they're not all exactly the same intrinsic brightness or have the same intrinsic color. This plot shown here on the right is data taken from the Gaia space satellite using, I think in this case, millions of stars. The color scheme here is essentially showing the density of stars in a given region. So how many stars have a certain brightness or color. It's whiter when there's more stars and redder when there are fewer, and some black points showing when there's only one or two stars available. So they just plot them individually. These are often divided into a couple main regions. This one down here where most stars live in white is kind of called the main sequence. The sun kind of lies somewhere around here. So this is where stars spend 80 to 90% of their life. Then as stars get older, they end up evolving up into this giant branch where they expand to become red giants. And finally, for some stars, after their giant branch, they can either end their lives, sort of in like a violent supernova explosion or turn into black holes, or some of them kind of just turn into these white dwarfs that live in this little region down here. The way that they were able to do this is by exploiting a phenomenon called parallax, which is to say that they needed an independent measurement of the distance to stars, not just their brightness. And the way that parallax works is that you can essentially leverage the fact that when you look at the same object from two different positions, it looks slightly different relative to the background. So in this diagram here on the right, you can see that when you look at, say, a star against a certain background from viewpoint A up here versus viewpoint B, the background that the star appears to be at is actually a little different from the location it actually is at. So from A, it looks like it's behind the blue one, and from B, it looks like it's behind the red one. This is actually something that we do all the time with our two eyes. So if you want to do like a quick test of this, you can just hold up your finger in front of your eye, and you can close one eye at a time and see sort of what part of my slides or of your screen are they actually blocking. And you'll notice that it actually does move depending on which eye you look at. And it's exactly this effect that we can exploit here on the Earth using one really neat trick, which is that we are actually orbiting around the sun. So that means that if you look at the sky 6 months apart, we've moved from one side of the sun to the other side of the sun. And that means that we're looking actually at a slightly different angle when we're looking at stars from one side than the other. So if we take observations over the course of an entire year, that means that we can actually measure how much this apparent motion of the star is relative to the background, and that gives us a measurement of the distance. And in fact, if you use the right units, you can essentially just do 1 over the measured angle, known as parallax, and that gives you a measurement of the distance. Then, using the inverse square law, you can then take these inferred distances to then get the intrinsic brightness. And so that's what's shown here on these plots, are a bunch of stars essentially that are located or have been shifted or adjusted to have roughly the same distance. That means if you get a new star, one that you have observed that you don't have a parallax for, and you want to know how far away it is, essentially what you can do is you say, well, I know what the color of the star is, so I can just draw a line. And this, I know that for stars of that particular color, they have this range in brightness. So therefore it has to be, somewhere in this regime. So that gives me a measurement and an uncertainty on the distance, depending on how common different types of stars are. So that's sort of the ideal. So that makes things a little bit more complicated, but it's not terrible. The problem is that life now gets much more complicated once you break this second assumption, which is that there's no material between us and other stars. This is a lot more difficult to deal with because it turns out that this material really can affect how stars look to us. This is often called what's known as the interstellar medium, or the ISM. And this is just that the space between us, between lots of stars, isn't completely empty, but actually filled with a lot of different materials, gas, dust, and other things. And even though dust is only about 1% of the interstellar medium by mass, it actually scatters about 30% of all the light, which is a lot. This plot shown here on the bottom is essentially in galactic coordinates. So the Milky Way plane sort of runs right through the center here. So this is kind of where you see most of the dust is. But you'll notice that this sort of shading here, which correlates with the amount of dust, this actually can vary quite significantly from place to place. And we're able to map this out by using data taken in the radio from the Planck satellite, which is another ESA mission. So this makes things really challenging because dust actually has two effects on stars. The first is that dust just blocks light, similar to like how if you're wearing glasses like me and they get dusty, you'll notice that things kind of get a little fainter. It's exactly the same with dust, like you're just blocking physically the amount of light. And so that process is known as extinction. So you're scattering the light away, you're blocking it from coming to us. It just makes things appear fainter. The next effect is called reddening, which is that the amount of light that dust blocks depends on the wavelength. It actually blocks blue light better than red light. So more red light can sort of go through dust, but less blue light does. And that means that if you're looking, for example, in blue wavelengths, you can have almost all the light blocked. But if you're looking in redder wavelengths, in this case, especially in the infrared, you can actually see through the dust to actually observe stars, behind it. And because of this effect, if you look, for example, on the edges of clouds like here, and you just zoom in, you'll notice that all the stars get really red. And that's because you're blocking all of this blue light, but not all of this red light. And so that makes the star appear redder than it actually is. So this process is often called reddening. So you have these two things that are happening, extinction and reddening. And what this means in practice is that rather than being able to say, oh, I have a star of a particular color, so I know what its true brightness must be, dust makes things complicated because now if you have dust in front of it, maybe it's actually a lot brighter, but it just happens to be there's a lot of dust in front of it. And so that makes it dimmer and redder, and means that the thing you observe is actually pretty far away from the true color and brightness of the star. So all of the purple regions now are, things that might be possible, like colors for and brightnesses for the star. So that's a real bummer. And particularly if we just look at the edges, that means we're dealing with two very different examples of what stars could look like. In one case, we have a star that has almost no dust in front of it. It has to be faint, it has to be close by, it has to be intrinsically very red. And this is a low mass star, something like, say, a K or M dwarf, if you know stellar types. In the other case, you have a high mass solution, which has a lot more reddening, has to be further away because it's intrinsically a lot bluer, or in this case, yellow. And this type of star might be something that looks a little bit more, say, like our sun, or even more massive than our sun. And you might notice again that if you actually look at this particular band also intersects this top part of this giant branch. And that also leads to this additional degeneracy, this confusion between a star that is on the main sequence like our sun, which is often called a dwarf, versus a star that's evolved, that's a giant. Those might have exactly the same colors, but one is a lot brighter, about 1,000 times brighter than the other. And so we have this uncertainty where we have no idea, essentially, does the star look like this? Does the star look like that? Or does the star look like this? And this is a humongous range in possible distances that a given star can occupy, because we don't really know how much dust is there. This is kind of what it looks like in terms of the end result. So this particular plot is showing on the x-axis the distance to a star, and the y-axis is essentially the amount of dust that we think is in front of the star. There are 16 different panels because this is for 16 different stars. And what's shown in red is kind of our best guess for where we think the distance to this particular star is and the amount of dust that's in front of it. The blue sort of shading here shows the uncertainty. These are all the possible combinations of sort of distances and dust that are acceptable fits to the data. And generating this plot is actually quite involved, and involves a lot of statistical and computational power to try and figure out what these look like, along with a lot of stellar modeling. What you can see when you zoom into it is that in some cases, there is a lot of uncertainty in terms of where a star might be, in terms of distance and how much dust is in front of it, or vice versa. In some cases, you have multiple possible solutions or guesses, although in some cases, you are pretty sure. So this type of behavior is what makes this problem really difficult to do. So Herschel was able to come up with a map because he ignored these things. But today we now know those effects are important. As you can see, they can have pretty strong effects on how far away we think a particular star is. So we really don't have a lot of, in many cases, a strong constraint on the distance to lots of these sources without some additional type of measurement. To get around this, a lot of astronomers in the past have tried to say, look, this is impossible. Getting distances to stars that look like the data in this plot here, this is hopeless to work with. What we're going to do is we're going to try and get data that's better. And so one of the ways that they went about doing this is by using these systems called masers. Now, masers are really cool astrophysical systems. They're called masers because they're short for microwave lasers. So think about like a laser beam, but rather than sort of red light or green, like something that you might use for stargazing, instead you're actually beaming them in the microwave. So kind of close to radio frequencies there. So these are really cool because they're very bright in the radio. And that means that they go through all the dust because the wavelengths are really, really long, even longer than sort of wavelengths at red light or the infrared. So we essentially don't have to worry about any dust for them at all. And because they're so bright, we can actually measure really, really precise distances to them using this parallax effect. And by doing so, we can then collect a lot of data on these by doing very, very time-consuming observations. So by spending thousands of hours on telescopes, we can painstakingly collect data for about 100 of these sources. And these masers are fundamentally what has allowed us to map the Milky Way out today. What's shown here on the right is the state-of-the-art set of masers, which we have data for taken from Mark Reed and his group at Harvard, at the Center for Astrophysics at Harvard University. And so what you can see here on the X and the Y axis is essentially a top-down view of the Milky Way. The center is sort of shown here as this little blue cross. And each of these different lines is showing different models for spiral arms that they're fitting for the galaxy. And all the dots here, these are the actual measurements of maser positions, color-coded by sort of which spiral arm we think they correspond to. But this is actually the state-of-the-art data we have for doing this type of work. So that's almost all of it. And you'll notice if you now look at the artist rendition we had previously, this is the data that is used to generate the plot that's shown here. That's the actual data that we have that gives us our best picture of the Milky Way, essentially these 100 data points or so. So this is sort of what we want to improve on, is asking, can we do better than sort of these particular observations? And how can we scale up to utilize lots of the data that we have today? One of the problems with using masers, as I described previously, is that they're not only are they really time consuming, you have to spend a lot of time trying to get good data for them, but they're also really, really rare. They only occur in specific astrophysical scenarios that require like the right conditions to be met. And you only get one of them. So for example, in like a star forming region like this, in this whole picture, there's only one maser that we have here, which is indicated with this arrow and sort of this dark band. But there are a lot of stars. Stars are common. You see, even in this image, there are hundreds, if not thousands of stars. And images are really cheap to obtain now. We have telescopes that just look at the night sky and take tons and tons of pictures. We have data on billions of stars. We have lots and lots of computing power. So these things that I showed you earlier that seem like they're negatives, we have these big uncertainties. This is very complicated. We don't quite know what stars look like. We can overcome them now just by sheer numbers because we have so many stars. And so that's the part of the talk that I'm going to skip over. Is a lot of my work is how we can combine sort of statistics and computation and machine learning and these other things to try and figure out what exactly these stars are doing. And that's a crucial part of the algorithm. But I think more important for this talk is to start seeing what can we do with all of that data and start looking at applications. So one of the things that we were really interested in doing is by using all these different stars to try and map out the local solar neighborhood. In particular, we wanted to look at something called these large molecular clouds. This is important for understanding, say, stars like our sun, because from our current understanding, we think that lots of stars are really born from these dense, dusty clouds of molecular gas. So what happens is over time, these clouds sort of collapse, and as they collapse, all this gas sort of clumps fragment into these little smaller clumps, and these clumps continue to collapse and fragment, and eventually they get dense enough that they form essentially tons and tons of stars. And so understanding these types of molecular clouds that we can see today allows us to better understand the conditions under which stars like our sun and many other stars have formed. The problem, of course, is that when you see a beautiful picture like the one on the right, which is a picture of the Orion Nebula, which of course is its own famous part of the Orion constellation, but it's also really interesting from astrophysical perspective. We want to understand properties of this. This 2D image is beautiful. We want to know, like, how big is it? How massive is it? How old is it? And all of these things require us, again, to get distances. So we need to know how far away it is. We want to understand the 3D geometry, the chemistry, so we can start to constrain many of these things. But getting distances to these things are actually really, really hard, which is a recurring problem in astronomy when you just have pictures on the sky. And this is actually where all of the negatives that I talked about previously actually start to become positives once you have enough data. When you have enough data, you can start to average over many, many stars. You can start to do really cool things. And one of those is that when you're trying to map out the distances to these clouds, you can exploit the fact that actually when you have stars that go through a bunch of dust, it actually does extinguish and redden their light. And that amount to which that happens depends on how much dust is in front of it. So that means if you have enough stars, you can actually use this effect when you observe the outcome to actually say, I can use the different reddening, the change in the color of stars and the change in brightness to actually construct a three-dimensional map of the interstellar medium. So by something that's really difficult to do for any individual stars, when you combine over many, many stars, allows you to construct essentially a three-dimensional map of dust in the Milky Way. This is a project that was jointly led between me and Catherine Zucker, who's a postdoctoral researcher at Harvard University and soon will be at Johns Hopkins. And what's shown here is kind of a basic demonstration of what we tried to do. So if you look at a particular region of the sky, this little cutout, this is showing a star-forming region called Perseus, again associated with the constellation. What you The white area is showing here essentially the amount of dust. So more white is actually more dust. If you look at a particular beam, we want to ask, like, how can you map out the amount of dust that sort of is along a particular line of sight in a particular region of the sky? And our model was really, really simple. Essentially, we expect that if we're looking at the total amount of dust, which is essentially the y-axis here, and then the distance on the x-axis, you're going to have some amount of dust in front of the cloud and some stars there. Then you're going to have this giant clump that's going to correspond to this particular cloud. And afterwards, you'll have stars behind the cloud that'll be more reddened and more extinguished because they have been behind all this dust. There's going to be some scatter because, of course, things are more complicated than we think. And of course, we're maybe going to have some weird oddballs. We want to have a way to deal with this. So we constructed a statistical model that tried to take into account all these different things, plus the uncertainties in all the individual measurements of the stars themselves. And so this entire project, again, was uniquely enabled by a lot of the stuff that, of course, is funded by taxpayers all across the world and also by universities. That has made it possible to really collect lots of really, really exciting data and also combine it with the advances in statistics and computation that have occurred in recent years, and to try and take these two things together to really try and come up with this stuff. So what does this look like? I think it's a lot easier to just show you. So my collaborators and I work really hard on coming up with some really cool interactive figures. So hopefully this comes across. Essentially, this is what we get as a result. So this is, again, showing the Milky Way with the bright spots being more dust and the dark spots being less dust, and 0 kind of being in the plane of the galaxy. Each of these different parts of the figure corresponds to different star-forming regions, these different molecular clouds. If you click on any one, it'll actually bring you to an interactive figure, which is shown here. If you scroll around with your mouse, you can see sort of what the value is and where you're located on the left. On the right, each of these different pixels corresponds to regions that we actually fit. If you go over each one, it'll bring up a plot that again shows you on the y-axis the amount of dust, on the x-axis the distance. Each of the individual sort of grayscale shows you some of the uncertainties, and the red dots again show you the best guesses we have for the positions of all of these different stars. As you can see, kind of highlighted with the orange arrow, that's sort of where we think the best fit distance to this particular region of the cloud is. What's really cool about Cepheus is that you can see, just by looking at the left and the right, that something happens between this top part, where the distance is close to only a few hundred parsecs from us, or about 1,000 light years or so, and the bottom. And you can actually see the transition where this occurs pretty sharply. If you look here, you see that there's one sort of easy solution, kind of located where it's pointed. If you look down here, suddenly you'll notice there are 2 steps. There's sort of one part of the cloud that you can see, sort of located a little bit to the left of the best fit line, and there's another located behind it. So this cloud structure actually has 2 parts. There's some foreground part. There's actually a background part where there's more dust in 3D sort of hidden behind. This is something that you don't actually see at all if you look at just the 2D map, but shows up really clearly when you look in 3D. This is one of the really cool features that you can do. And of course, because we're transparent, if you mouse over every single pixel, we not only give you the best fit parameters for everything, and you can see our model, you can see all the data, and you can explore this for every single thing that we actually fit here. So if you click on any region, it'll pull up all the results from that region, and you can go through and investigate and see for yourself how much you believe what we've derived. So that's very exciting. And again, if you want to link to some of these things afterwards, I'm happy to share my slides, and you can all go explore these for yourself. All these figures are public, so you're welcome to click around. The upshot is that when you compare these distances that we derive, essentially which are based on stars, which are common, versus these Messier distances, which are based on these very particular astrophysical objects, and you ask how well do they compare in regions where we have both, we find really, really good agreement, essentially exactly 1-to-1, so perfect agreement between the two, out to a few thousand parsecs, which is great. This means that this method, which we can do, which relies on sort of cheap, plentiful, common data using common stars from all these images that we have, from lots of the images that probably you for example, take when you go and go stargazing, that type of stuff is enough for us to do this type of really exciting science at scale. One of the things this led us to do is that when we now took this approach and applied it to just over every sort of star-forming region that we knew about, we could derive a homogeneous set of distances to all of them using the same technique, the same type of data, in particular at resolution that we were not able to achieve before. And what we found was something pretty interesting. So for example, what's shown here on this plot again is a top-down projection, sort of X and Y, with the sun at the center here. So that's sort of in yellow. And what you can see is in the black background is kind of a measurement of the dust. And each of these different blue points is a distance estimate that we derive to a bunch of different regions, all of which have different names associated with different constellations or star forming regions or whatever. And the two interesting features is that the first is you'll notice what's called a local bubble, which is that right around the sun, you can see it in more detail actually if you zoom on the bottom right, there isn't actually a lot of dust at all. And this is an interesting feature, but you see that there are these two big curves here that correspond to a lot of star forming regions. And this is what's known as Gould's belt, which is just the fact that over 100 years ago, Gould realized that a lot of these features of places where they're forming stars kind of seem to form this ring on the sky. But what we found actually was that this belt seems to actually really be subsumed by a much bigger feature, this gigantic sort of connection that appears to run like right by the sun. And this feature is what we called that we discovered is what we call the Radcliffe Wave, due to the fact that it was discovered at the Radcliffe Institute at Harvard from the lead author, Joao Alves, who's now at the University of Vienna. And the Radcliffe Wave is super interesting because it turns out that it actually corresponds to, let me just get out of this. This is another 3D plot that we have of the wave. And you can see here we've colored in red. A lot of these other regions are colored in sort of blue or green. And what's kind of amazing about what we found here is that this region is really long and contiguous and kind of has this feature where it looks almost from the side like kind of a sine wave, like this undulating wave throughout the galaxy that really looks like it's oscillating in the plane of the Milky Way. It's really well localized if you look at it on the end. And this is not something that was really predicted from any type of model and that we really discovered serendipitously in the data. One thing that's really exciting was that it turns out that when you look at sort of the best fit measurements to the local spiral arm, it turns out that actually our Radcliffe Wave corresponds almost perfectly with what we think the local arm of the Milky Way is. And in fact, places where we have major measurements, which are here shown in blue, our measurements from red actually agree almost perfectly. So our data essentially is a very high resolution image of the local arm. And from our best fit modeling, we actually think that this corresponds to actually the majority of mass and what we think of as the local arm around the sun. So it's really concentrated not in this diffuse structure, but this really thin kind of ridge-like wave thing. And we still aren't quite sure what its origin might be, but it appears to be a real thing. So this is really exciting because it kind of shows a new discovery that we didn't expect that overturns an old paradigm of how we thought sort of stars formed and behaved near the Milky Way for about 150 years. And this, again, wouldn't have been possible kind of without lots of these different advances kind of coming together, in recent years. Finally, I want to just move in the last part to talk about some efforts we've made to sort of map out the galaxy at large. In this case, you can think of, if you're looking, again, this is a slightly different artist rendition, it's a little older. What we've done so far is kind of try and map out local structure in the Milky Way using stars like this, using these star forming regions. And what we are instead interested in doing is, can we just map out everything that's nearby the sun? And so this led to what we call the Augustus Catalog, which is trying to use the same sort of tools to map out about 170 million objects using about a little under 1 million CPU hours. And so the distribution of what stars we're looking at are sort of shown here on the right. Again, this is in sort of galactic coordinates. So you'll notice that there are two regions missing. One is that we cut out the plane because there are a lot of stars in closer to the plane of the galaxy. And this is meant to be just like a proof of concept. So just showing that we could actually do this at scale. This huge region here, this is actually the south, so of the Earth, of the sky. And that's just because the telescope that we were using for a lot of this data is based in Hawaii. And unfortunately, we can't point the telescope down to look through the actual planet. And so we just can't get data in a particular region of the sky. This is something that we're hoping to fix by now moving to data that's going to be taken from space and sort of future work. So I think, as a statement, this is what we consider a proof of concept, because we ultimately really are thinking about, can we get distances to all sort of like 1.5 or 2 billion stars that we actually have data to now? This is just meant to be kind of like a trial run to see whether this actually works. So one of the ways to look at this is to imagine taking like a slice around the sun. So, taking all stars that are some distance away from us and seeing what they look like. And if you project that onto sort of these same two-dimensional plots, you get something that looks like this. And so one thing that's really cool here is that the color here corresponds to essentially the number of stars that we see in a given region. You can't see it, but there are little arrows on this diagram showing where the stars are moving based on measurements we have from the Gaia satellite. And what you can see right away is that there is this boundary sort of between the disk and the halo in terms of where stars are located, which is great because that shows that we're able to recover overall galactic structure. If you look further out, you start to see some more interesting features. In particular, you'll notice that actually now the sort of motion of stars way up here is actually much more random. And this is because we're now getting really far into the stellar halo. We're looking at very, very old stars, and their motions are essentially random directions kind of in a sphere. On the left here, you'll see this sort of large contiguous region where there looks to be a lot of motion that's in the same direction. And this actually is telling us that our Milky Way, the disk actually kind of is flaring up and getting bigger the further away we go, rather than smaller. So this flaring actually shows up really clearly when you look at the velocities of these stars, the fact that they're all moving in kind of the same direction and at a large speed. And this is something that we know about, but it's great to see that it actually shows up in the data and says that our Milky Way is not like some flat pancake. It actually kind of flares out at the edges. It has sort of warps and ripples and all this other structure that we're just starting to dig into, in real detail over the last, 10 or 20 years. One of the coolest ways I think to visualize this is to actually look through an interactive version. And for this, we drew a lot of inspiration from wind maps and patterns that are used to visualize like currents and heat maps on the Earth. And so this is, I think, our most ambitious attempt to visualize what some of this looks like. So what's shown here essentially is what we call all sky. So this is now showing, again, the same projection, these different streamlines, if you can actually see the animation, shows the bulk motion of stars in sort of a cut on the sky and how they're moving relative to us at a given distance. If you click around, you can kind of see what the results are for various regions, and the coloring corresponds to the velocities. But you can change all of this. One thing I love is that I don't know about you, but I like looking at things on a globe because we live in three-dimensional space. And if you switch everything to look like on a globe and you ask, where are we missing data? It's now very clear why we don't have data in a certain part of the sky, because it's all located, in the south. So it's much easier to see. It's also easier to see where we don't have data for the planet, for the plane. You can also look at stuff much clearer in terms of how structures are moving. So this is now mostly flat. You can change the density to see where we have lots of stars. You can highlight particular regions where we can see like there's an overabundance of stars in certain locations, which corresponds to known sort of star clusters. You can instead plot things like chemical composition, age estimates that we're able to get. And in particular, if you look at, say, for example, some of these really far out, you can actually see examples of large substructures in the galaxy. Like, for example, this really coherent feature here, which is actually a visualization of the dwarf galaxy Sagittarius, which has collided and is merging with the Milky Way. So this is the remnant sort of tidal debris that we're able to see sort of show up in our data. If you look really close by, you can start to see lots of other things too. So for example, if you look just within sort of 0 to 2 kiloparsecs of us, you see this really interesting structure in terms of how stars are moving. And the reason that you see this is because if you imagine that you have all these stars kind of orbiting around the galaxy, around the sun, we're all kind of moving together. And so if you look directly along the orbit, you don't really see the stars move at all because you're all kind of moving in the same direction, right? It's like when you're moving on next to each other on the street, and all the cars are moving together. It looks like you're all standing still. But as soon as you look kind of sideways at something that's not moving, then suddenly you see all this motion. And so if you look sort of perpendicular to sort of the average motion, or if you look sort of completely upwards or downwards, you can start to see all these stars kind of stream past you in various places. Other than at the pole, there's some like small problem in terms of plotting exactly at like, right above us. So again, this is like a publicly accessible website that you can play around with. So you can again click on the link, but this is, I find, super fun. You can explore lots of different projections. You can toggle on some grids. You can sort of click around to see how quickly stars are moving, or how many stars that, on average we find in a given region, what the direction of things are. And this visualization is kind of one way of trying to interpret sort of the, over 100 million stars we've tried to use to start to do this work. So just to wrap up quickly, in summary, essentially, I tried to talk a little bit about some of the history and background of, why we're interested in mapping the Milky Way, and sort of all the way from Herschel to today. So a nice, 200 plus year history of looking at this. I sort of skipped over a little bit, but showed some plots about, how exactly it's important to infer lots of these stellar properties, and the difficulties in actually figuring out how far away stars are from us. Turns out not to be so easy. How we use these to start to map out sort of lots of these molecular clouds in the solar neighborhood. And we discovered some really cool stuff that is sort of changing our view on what we think sort of local spiral structure looks like in the vicinity of the sun. And finally, sort of brief forays into trying to map the galaxy at large. And this, for us, is very much a work in progress, since we really are interested in trying to scale up to the whole data that we have available now. So, the step from 100 million to over 1.5 billion stars is on the horizon, and we're sort of hard at work at trying to get those run through and analyzed, and hoping to get those, new sort of maps out in the next year or two. So that's all I have as a summary. And, I'm happy to take any and all questions or chat afterwards. And thanks so much for giving the opportunity to speak. And hopefully this was exciting and fun.
Well, thank you very much, Josh. That was amazing. A lot of computing power required for some of the things that you're doing there. Absolutely.
Yes.
So a question from Joe Holmes. How effective is parallax, considering how very far the stars are from us?
Yes, that's an excellent question. So for a lot of stars, actually, the parallax constraints are essentially don't provide any information at all, except to tell us that the star is far away. So all the measurements are roughly essentially consistent with zero, but it at least tells us the star isn't close. Because if the star was close by, we would measure a parallax, and we would actually see that. So the fact that we don't measure a parallax tells us it's at least far away. That amount of information is very limited, but it actually can be very important for distinguishing some of the sort of confusion between different stellar types and evolutionary phases that are important when doing this mapping. So they actually matter a lot.
Okay, thank you. I don't see, here's another one that's just come in. How will the James Webb Space Telescope improve this type of research in the future?
Yes.
Commander.
So the James Webb Space Telescope is not necessarily designed to do sort of this really large survey work. It's really designed to look at some smaller regions in a lot more detail. But what we are really excited about, having James Webb to do is to be able to study some particular types of stars, especially in other galaxies like Andromeda, in a lot more detail to better understand how we can improve on the stellar models that we use to derive lots of these properties. So we're hoping to essentially use really, really good observations of a small number of stars to go back and improve on the model and the theory, so that we can then expand it to improve measurements to many more stars.
Okay, Michael has a question. Thanks for a great talk. He says, for the last section with the full galaxy visualization, what is the time step assumed for the motions?
Yes. So those are, we're assuming pretty large time steps. So the typical motion for stars, like necessary to actually like change their position in sort of what we can observe, is usually very, very long. So we're essentially showing you bulk motions over hundreds of thousands, if not billions of years. And in general, I want to emphasize that really the lines there are meant to kind of guide the eye to sort of show what the population of stars are doing overall, rather than what any individual star is doing. So you can think of it more like just trying to visualize like broad currents or something, rather than visualizing exactly how quickly any particular star is moving.
Okay, a follow-up question from the same person. He says, how does this last visualization shed light on dark matter?
Yes. So one of the ways that we are starting to understand dark matter is we want to perform more and more tests to understand how essentially dark matter impacts the particular motions and kinematics of stars. So The thing that we do know is that we measure, broadly speaking, the bulk motion of the rotation curve for galaxies, which is the bulk motion of sort of the dust and gas and stars. That sort of changes the fact that that behavior looks different from what we expect at very large radii is one of the peak evidences for dark matter that we have. Right now, the main focus for dark matter is trying to constrain what type of dark matter it is. Is it cold dark matter, which is kind of very clumpy, or warm dark matter, which is less clumpy? The effect that that has on the overall distribution of stellar motions and substructure in the Milky Way can provide one of the clues here. But it's starting to get sort of into looking at a lot more detail about that type of motion that can sort of be easily summarized.
Okay, so it's got two more questions, and then we'll move to the break. So from Eve, are you collaborating with the Milky Way at Home project in any way?
I'm not collaborating with them at all, but I'd love to hear more.
Okay. And then Dennis O'Farrell, are we getting better parallax measurements with space probes in the outer solar system?
So essentially so we are getting better ones with Gaia. The issue with the space probes in the outer solar system, I think like say Voyager, for instance, is that they weren't really quite designed to do these types of measurements. So what they are able to do is to give us some sense of like how the longer baseline that they have is able to help for specific observations, but are not really super useful for a lot of other stars. They are actually very useful in probing a lot of other sort of, especially like physics about like the helio sheath and sort of the influence of the sun and the solar system and the extent of that, but they aren't as helpful for sort of improving parallaxes to other stars.
Okay, super. Well, thank you very much, Josh. We really enjoyed your talk. And if there's other questions, I'll have folks send them to you via the chat box.
That sounds great.
Okay, thank you. So there we go. Chris, if you can bring up your slides, we're going to move into a 5-minute break. And we have the Messier and Moon Challenge. There we go. So go to the next slide. So over the next 5 minutes, see if you can figure out which Messier object this is and which moon object this is. We'll give you the answer after the 5-minute break. We'll see you then. Okay, folks, welcome back from the break. Okay, so we'll just move on to the next slide then, Chris. So here is the answer to our Messier and Moon challenge. Messier object is Messier 66, spiral galaxy, and we for the moon it's the Hadley Rill. So hopefully one or two of you got those. So we're just going to move on to Paul Klauninger, who's going to be talking about the observing and imaging the solar eclipse. Paul's going to turn his video off. He's out in the boonies. And so I'm just going to bring up Paul's picture on top of my face. Just give me a second here. But you're going to hear his voice. It's not me talking. Okay. There we go.
You look better and better every day there, Dave.
Yeah, thanks.
Okay, I'm good to go. My audio is good?
Your audio is good, yeah.
Super. Okay, well, hi, everybody. I'm glad to be able to talk to you tonight because, especially with the timing we have here, because as you undoubtedly all are aware, in 5.5 days from now, we have a rather rare event happening that we can see from our neck of the woods, and that is a partial solar eclipse. Next one, please. So I'm going to give you a bit of background on solar eclipses, especially for those that may be new to our club or new to astronomy generally, just so that you know what we're talking about here in terms of what these solar eclipses are and why in fact they happen. So a solar eclipse. Oops, hang on a second. I have a. Okay, I had something come up on my screen. Sorry. So solar eclipses are rather neat events dealing with the sun and the moon, and they can only occur when the moon is in its new moon phase. And just an aside here for a second, I'm going to throw a lot of stuff at you here with the slides that I've prepared because I want you to be able to understand this. This is a beautiful event that we're going to see, hopefully if we get some clear skies. But it's also potentially dangerous, and so I've made this presentation available. I asked Mick Wilson to put a PDF version of this entire presentation up on our website there, and you can access that and download your own copy there because there's some how-to stuff and some tips and hints, and you can review those later at your own leisure before the event happens. So that is available just right off the homepage from the Ottawa RASC website. So, but I'll step through this and then take any questions afterwards. So as I said, solar eclipses can really only happen when the moon is in its new moon phase. And these eclipses are rare because the moon's orbit is tilted with respect to the path that the sun travels, apparently travels across the sky, which is our orbital plane of our own planet. The moon's orbit is tilted is actually about 5 degrees to that plane. And so the eclipse can only happen when a new moon phase occurs, and when that occurs very near to or at the node, which is the point where the moon's orbit crosses the apparent motion of the sun across the sky, as you can see in the diagram here. When a new moon is further away from the node, you either get a partial eclipse or no eclipse at all. So that's why they don't occur. Eclipses don't occur every month because of that tilt of the moon's orbit. Next one, please. So interestingly, our planet is rather unique like this. We have a very large moon in relationship to the size of our planet. And we live in an interesting point in the history of our planet and the solar system generally. Because at this point in time, as seen from the surface of the Earth, the sun is about 400 times larger than the moon physically, but it also happens to be about 400 times further away. So as a result, when we see the sun and the moon in the sky, to our eyes, they appear to be about the same size, about 0.5 degree across. And so when those orbital paths align and it's a new moon, we can actually get the moon almost precisely covering the sun. And this is unusual in the solar system. I mean, all the planets that have moons, Jupiter, Saturn, and Mars, they all get eclipsed by their moons, but those eclipse paths only block out a small portion of the sun as seen from those planets. Here on Earth, we get this beautiful occurrence when the conditions are just right, where the moon can physically cover almost exactly the whole solar disk, and this allows us to see some really beautiful stuff. As I say, this is a unique point in time in history, because since the Apollo landings back in the 1960s and 70s, we've had the capability, because of instruments, reflectors that were left on the moon's surface, to measure the distance to the moon very, very precisely using lasers bounced off those laser targets. And as a result, we know that the moon is gradually moving away from the Earth at a really small distance, about 3.8 centimeters, or about 1.5 inches per year. It's amazing that we can actually measure it that precisely, but that's modern technology for you. At any rate, this movement will continue, and in the future, that alignment, that coincidence of sizes will no longer be relevant. All we'll see in the distant future from the surface of the Earth are annular solar eclipses. And in fact, what we have happening in 5.5 days is actually an annular solar eclipse. It's not a total solar eclipse, and I'll show you the difference of that actually right now. So next slide, please. So the moon's orbit is not only tilted to the plane of our own orbit around the sun, but its orbit is elliptical. It's not perfectly circular. So at some points in time, we get what we call supermoon when it's a full moon. And we get this very, relatively large looking moon in our sky. That's because at that point, the moon is at its closest point to the Earth, or closer to the Earth in its orbit than usual. On the far side of that, if that new moon, or if that full moon occurs when the moon is at its apogee, or it's furthest from the Earth, the moon looks correspondingly smaller. And it's this last scenario, when the moon is near its apogee, that leads to an annular solar eclipse. So I'm going to show you what that diagram looks like. Next one, please. So back in 2017, we had an enormously beautiful total solar eclipse of the sun happening. We weren't on the path of totality here in Ottawa, but if you were lucky enough, like I was, to travel down to the States and put yourself in that path, we got just a phenomenal view of a total eclipse of the sun. And as you can see from the diagram here, what that means is that the moon was at the right distance from the Earth when it was in its new moon phase, where the shadow cast by the moon came to a focus basically on the surface of the Earth. And that you can see that dark band mark the path of total eclipse. That is the umbra. And that is a very narrow path, typically, about, give or take 100 kilometers or so across, sometimes a bit larger, sometimes a bit smaller. We have a much larger surrounding area called the penumbra, which is the area surrounding the total eclipse, where you can see a partial eclipse. And that's what we had happening in Ottawa. We were in the penumbra of that 2017 total eclipse of the sun. Next one, please. So total eclipse of the sun is remarkable. And if you've never seen one, make sure you put that on your bucket list. You've got to see at least one of those once in your lifetime, because they are like nothing else you've ever experienced. It's ghostly, it's ethereal, and it sends shivers down you. Literally, actually, when I was down here for that August eclipse in Wyoming, in 2017, when we were observing that, the temperature dropped about 10 degrees Celsius during the time of the total eclipse phase, and it was noticeable, and it did literally give us all goosebumps. It was quite phenomenal. And not only that, it gave us phenomenal views. Some of the shots that you see here, this is a collection of some of the images I took while I was down there. You'll get Bailey's beads, and you get the diamond ring effect, and you get this beautiful solar corona, and it's the corona that is really remarkable, because if the moon didn't fully cover the disk of the sun, you would never see the corona. The corona is many, many times dimmer than the sun itself. And so if there's any sunlight poking out over the rim of the moon, you don't see that corona. So the next slide, please. the next slide actually shows you what you can see in a total eclipse. This is a view I took, and basically this is a view without filters. This is the only time in an eclipse of the sun where you can actually look at the sun, at the eclipse in progress, without glasses, without special filters or solar eclipse glasses. For that couple of minutes of totality, when the moon completely covers the disk of the sun, the sky darkens, and basically the moon is blocking out all the harmful rays of the sun that would otherwise damage your eyes. This is where it gives you that really otherworldly feeling, because you can see stars during the daytime. You can feel the temperatures drop. If you've got dogs or other animals around, they start going a little bit nuts because they really don't know what's happening. So it is a phenomenal event. And in fact, in 2 years from now, we have a total eclipse of the sun passing very close to Ottawa. In fact, if you put yourself down along the St. Lawrence River, you'll actually put yourself in the path of totality, and you'll be able to see, hopefully, if the skies are clear, you'll be able to see a view like this. So this is a total eclipse, but this is not what we're going to see in 5 days from now. Next one, please. So what we have happening in 5.5 days is an annular eclipse. The moon in its new moon phase is further out in its orbit, and so its shadow, its complete shadow, falls a little bit short of reaching the Earth, as you can see in the diagram here. And instead, if you're in the path of annularity, you're in what's called the antumbra, and you'll see an annular eclipse of the moon, which is essentially a dark center with a complete ring of light around it. But again, that's not what we're going to see here in Ottawa, because we're not in the path of annularity, but we will be in the penumbra. So we will get, in fact, a partial solar eclipse. And a partial solar eclipse, when you're dealing with an annular solar eclipse, looks exactly the same as a partial eclipse when you're dealing with a total solar eclipse. Right? Partial is a partial. So next one, please. So this is what's happening in 5.5 days. The eclipse actually starts in northern Ontario, and as the Earth turns and as the moon moves in its orbit, that path of annularity, the dark shading that you see here, moves to the north and to the east. Next one, please. And if we look at the global view, you can see that path reaches up and actually goes right, part of it actually goes over the North Pole and terminates in eastern Siberia. So not a lot of people are going to be able to see the annular phase of this eclipse, because there's not a lot of towns or roads up in any of that darkened area. But a wide swath of the country will see a partial eclipse, and that is what we're going to get here. Next one, please. So this is an image of a partial eclipse that I took a few years ago, 9 years ago actually, and like the one we're going to see in a few days, this occurred very close to the sun being very, very close to the horizon. In fact, the sun was setting. The one we're going to see in 5 days is the sun rising, but you could see the eclipse was there was just a little piece of the sun being etched out by the moon as it was setting, and it was very close to the horizon. That's why I've got tree branches eclipsing part of the sun. So this is where I want to start nagging you, if I can use that term, about being super, super careful with this eclipse. There is no point in time for this eclipse that you're going to see that it is safe to look at this eclipse with the naked eye. And this is why I stress this in particular for this eclipse, because this whole event occurs very close to the horizon. And as most of you are probably aware, if you're a morning person and you're out just at sunrise, often you'll see low-hanging banks of clouds. You know, the sky may be clear up above, but you get low-hanging banks of clouds and things like that. And if there's any low banks of clouds like that, and you see the sun rise through them, you'll notice that the sun is quite dim, or can be quite dim, depending on how thick those clouds are. And it tends to be a bit more reddened. That is not a signal that it is safe to look at. Some people think it is because a lot of the sunlight's being blocked out. The truth is, not nearly enough is being blocked out to protect your eyes. And even though visually some of that the sun may appear to be dimmer, you're also dealing with infrared light coming from the sun, which you can't see, but which much more easily penetrates any low-hanging cloud. So even though the sun may be looking a little bit dimmer if it's close to the horizon, there's still enough infrared light coming through those clouds and into your eyes that if you're not protecting your eyes, it can literally cook your retina. And I don't say that to be dramatic. I say that to be realistic. This is a dangerous thing to look at. Early observers of eclipses, and especially with telescopes and that, actually became blind, and still at this point in time, people look at eclipses during total, or a little bit, few seconds or minutes before or after the moon goes into a total eclipse, and they get blind because this damage happens very quickly. Remember, your eye has a lens in it, and if you've ever taken a magnifying glass and tried to burn your initials into a piece of wood or set a piece of paper on fire, the lens in your eye is going to do the same thing to the back of your retina. It's going to cook your retina because it's going to focus whatever light's hitting it onto a smaller spot, and it'll act just like a magnifying glass. I cannot stress this enough. Even short glimpses are enough to damage your eyes. Now, I'm going to harp on this a little bit more with the next slides that I'll show you about how to look at it safely. But anyway, next one, please, Chris. We'll show you what's happening in Ottawa in 5.5 days. So this is a great website if you want more information and if you want to see an animation of what we can see. It's timeanddate.com, and you can set your location for anywhere you want, Ottawa, or you can even set it with a map and set the latitude and longitude. And it'll simulate the eclipse as seen from that location. So it's an excellent reference, and you can actually look at past and present and future eclipses on that site. So here's the data for our Ottawa occurrence. As you can see from this chart, the eclipse actually starts about 45 minutes before the sun rises in Ottawa. So when the sun is rising at just about 5:15 in the morning, the eclipse is already in progress. And about 25 minutes later, it reaches its maximum extent. In other words, the time when the most part of the sun is covered by the moon. After that, the moon will start moving away from the sun, and by an hour after that, at about 6:40, the eclipse will be over. And if you look at the two columns on the right-hand side, you'll see the direction that this occurs in. You can see the various degrees. Sunrise occurs at 55 degrees and progresses to the east, and it ends at 69 degrees. If you're not familiar with those direction coordinates, 0 degrees is due north, and the degrees increase as you look further east. Also, the altitude, you can see here, the moon is, or the sun is rising. 0 degrees at about 5:15. When the eclipse reaches its maximum extent, it's only going to be about 3.2 degrees above the horizon. That's not very far above the horizon, and we're going to need a mostly clear sky to be able to see this. So it's a bit of a challenge object that I'll add to this month's challenge objects. It's going to be tricky to observe. If you want to see it right from sunrise, you're going to need a location where you have a nice, clear, open vista to the northeast, almost right down to the horizon. So, there's many spots along the Ottawa River that would probably be suitable, or if you're surrounded by big cleared farmers' fields, that may also work for you. But that's what you will need. If you can't get out to a location like that, but still want to see part of this eclipse, you may not see it at its maximum, but before the eclipse ends, you'll see that it's already about over 12 degrees above the horizon. You'll just see less of the sun being covered by the moon, but you will see part of the eclipse. And that might be a little easier for some in terms of time-wise as well, since it's not 5:15. The eclipse ends at about 20 minutes to 7. Okay, so what can we expect to see from Ottawa? Next one, please. So when the sun rises, this is what you will see. If you've got a clear vista down to the horizon, this is the phase that the eclipse will be in at about 5:15 in the morning on Thursday. You see how much is covered here. As it progresses, 25 minutes later, next one, please, Chris, we'll see the maximum extent of the eclipse, and that's what you're looking at. And you can see that the crescent itself actually kind of seems to rotate or shift, and that's because the moon is moving basically off to the left hand, off the disk of the sun. So this is at 5:40 maximum eclipse, and next one just shows a phase of the eclipse around 6 in the morning as the moon continues to move off the face of the sun, exposing more and more of the disk of the sun, until finally, with the next slide, please, Chris, we get back to an uneclipsed sun, and the eclipse is over. These images, by the way, that I've shown you, I assembled these from actual images I took of the partial phase in the 2017 eclipse, and then just rotated them to the correct perspective as we see from Ottawa. So just if you're curious, that's why you got sunspots on this particular image here. We did have some sunspots on that 2017 eclipse. Okay, next one, please. So question is, how can we watch this eclipse safely? I've already warned you that this is dangerous. I will warn you again because I pretend I'm your father or your mother tonight. And I can't stress this enough. I'd hate to see anybody come out of this event with any kind of damage to their eyes, and it is very easy to do. So if you don't have any special equipment, if you're new to this, the best way to do it is to project the sun. You're not going to be looking at the sun, but basically you're going to hold up a piece of cardboard, as you can see on the illustration at the lower left. It's going to have a pinhole in it, and you need another sheet of paper or cardboard behind it to project an image of the sun. The sunlight will stream through the pinhole, and it will enlarge as it travels towards the piece of paper. The further back the piece of paper or cardboard is from the one with the pinhole in it, the larger your image will be. And you can see a couple of different ways of doing that. Another interesting way, if you have a pair of binoculars but no filters, is to use your binoculars. You can see that the binoculars have been twisted or held so that normally the end that you would observe with is facing the sun, and you're projecting the image of the sun out of the other end of the binoculars, again, onto a sheet of paper or cardboard to get an image of the sun. And for this, it also helps to cap one side of the binoculars there, so you only get one image of the sun. Next one, please. So if you do have a telescope, you can also use your telescope. If you don't have a filter, you can use your telescope to do the same things the binoculars were doing. In other words, to project an image. You would have an eyepiece in the telescope, and you would hold a white sheet of paper or cardboard behind the eyepiece to project this image. Now, again, don't let anybody look. If you're sharing this event with somebody, don't let anybody look through that telescope unfiltered, because again, that will fry your eyes in moments. Okay, and be cautious if you have a finder scope mounted onto your telescope, because that too will do the same thing. And if you've forgotten to keep the caps on that or something like that, and you're working around it, you may find that, I don't know, your jacket or your skin or something might get burned by the fact that your finder scope is focusing sun rays unintendedly on your skin or something. Andrea also, I was trading some notes with Andrea on this eclipse, and Andrea sent this rather unique picture. I've never seen this done before. Unique picture on the lower right. She used a colander to project the sun, and so you get multiple images of the sun being projected. Right, she did it right down onto the ground, that's an interesting effect. In her case, a lot of little round dots, but when the sun is eclipsed, you'll get a lot of little crescents there. I don't think you'll be able to project it on the ground because of the low sun angle, but you could use something like that, and again, project it onto a piece of cardboard held behind the colander. So nice one, Andrea. It's a rather unusual approach. Okay, next one, please. Actually, Chris, can I roll it back one more? Sorry. The image at top center there shows the same thing that the diagram on the left shows, but it's using a right angle prism to make the viewing a bit more comfortable. Again, this is something you can do. You obviously wouldn't be using filters on this, and you are projecting the sun image, as you can see with the gentleman holding the sheet of paper. Again, the farther back you are away from your right angle prism with its eyepiece, the larger that sun image will be. But again, this can be tricky and a bit dangerous. Do not look through the eyepiece. Okay, next one, please. So this is an interesting one I found from the Canadian Space Agency. Actually, this is a simple solar eclipse projector that you can make, maybe with your kids or something. Probably take you all of 5 minutes to do this, and all you really need is something like a shoebox and a piece of aluminum foil. So what you see here is that there's just two holes cut into the end of the shoebox. One is called the viewing hole, and the other one is called the sun hole. What you wind up doing is just taping a piece of aluminum foil over the sun hole, and then taking a pin. You don't need anything much more bigger than a pin. Poke a tiny hole in that aluminum foil. Then you turn your back to the sun, look through the viewing hole, and try to aim it so that you'll eventually see an image inside the darkened box of the sun projected on a white piece of paper that you've taped to the inside, the back of the box there. So you basically would put the lid on it, obviously, to keep it nice and dark in there. So you're going to have a very black view inside there as you do your viewing, and you should get a pretty nice darkened image of the sun in that shoebox. This is advantageous because when you do the other methods of projection, don't forget you're in daylight, and so those images that you project onto a piece of cardboard or a piece of paper are going to be competing with the ambient light of the day, and so they're not going to be super bright, I mean, depending on your scope, of course, and how close you hold it. But certainly something like this will give you a very dark interior, and you should see a noticeably very bright image of the sun when you've got that alignment correct. So an interesting project that really probably take you all of 5 minutes to make. Okay, next one. So the primo way to view this, if you're fortunate enough to have solar eclipse glasses, is to use these, because with these glasses you can then safely look at the sun while the eclipse is in progress, and what you'll see is very similar to the images I was showing. You'll see a sort of an orange-colored sun being eaten away by a piece of the moon there. The thing with these solar eclipse glasses is you need to be very careful, especially if you've got an older pair or something like that. You want to make sure that there's no tears in the material, because the material itself is kind of a flexible plastic. It's so it's not glass or anything, and it is, it's a relatively delicate thing, and I don't know how well they hold up over time. But what you don't want is any like pinholes or things like that in those, or scratches, that type of thing. You want to make sure that the thing that you're going to look through completely shields your eyes. Also, if somebody in your family is aware, or you have access to welder's glasses, those are also suitable solar eclipse glasses, provided that they are in shade grades either 12, 13, or 14. That gives you enough filtration to block any of the harmful rays of the sun. Okay. Now, these eclipse glasses were widely available during the 2017 eclipse, because that was such a tremendous event and easily visible during a very warm period of the year, and nice and high in the sky. I know that Focus Scientific was selling them, and I think they were actually giving them away at various museums there. I don't think there's quite the same level of enthusiasm for this early morning eclipse, and it's not going to be as spectacular. But if you're interested in getting a pair of these, you may check with Focus and see if they have any in stock. But these are nice glasses to use, and they really make viewing the eclipse a treat. Next one, please. So the premium thing that a lot of us older hands are using when we're taking pictures of the sun or just observing through binos or telescopes are glass filters. These are much more robust than the solar eclipse filters. They come in pre-mounted cells of a certain size to fit your particular telescope or pair of binoculars. Obviously, you need two pair of binoculars and one for the front of your telescope. These are mounted on the front, so they will block basically all the sun, 99.9999% of the sunlight from actually even entering your telescope. But again, if you've got one of these, you want to make sure there are no scratches or cracks in them at all. They need to be a solid, uniform surface. And also with solar filters, you have to be cognizant that there are different grades of these filters. Only the Type 2 and the Type 2 Plus are intended for visual use. There is a Type 3, but that is intended for photographic use. It's not suitable for your eyes. Okay, and next one, please, Chris. All right, solar films. So these are very popular. They're made by various different companies. The most widely known one is from Bader Planetarium, and they make a solar film that is very popular. You can buy these either again in pre-mounted cells that are specific of specific sizes for your particular optics, or you can buy bulk sheets of them and make your own. A lot of us like to do it ourselves. And so we make custom fittings either for our finder scopes or that type of thing. And so you can buy these sheets. I know Focus normally sells them. Again, I don't know what he's got in stock. I should have checked with him, but you can give them a dial if you're interested. But be aware, just like the glass solar filters, there are different grades of these filters. Okay. So the one that's safe that you can actually use to make your own solar glasses if you want is called the Bader Astro Solar Silver Gold film. And this is specifically developed for visual observations at what we call at zero magnification. In other words, with the unaided eye. Okay, so you can make your own solar glasses with this, and you'd be good to go. Now, they have another grade, which is very common, and that's the solar safety film with an optical density of 5.0. This can be used for visual and photographic solar observations, but only through additional optics. In other words, this is intended to be used to make a mask for a front-mounted filter, either on your camera lenses or your telescopes. The additional magnification of your optics spreads out the light of the sun, so you're not seeing the full concentrated disk of the sun in one go. And so that's why these are safe to use. This grade is safe to use with optically as well, provided you're doing it with a telescope. Okay. And then the final one I've got on the list there is the Astro Solar Photofilm 3.8. This is only used for photographic purposes, and even there, only in conjunction with fast digital video cameras. Okay, this allows more light of the sun in and is not safe for visual solar observing, either as used in solar eclipse glasses or as a filter in front of your telescope. You cannot use this. Again, if you're looking to make your own filter for in front of your telescope, go with the optical density 5.0, or you can also use the silver and gold. Okay, next one. So I was surfing around looking for all the different weird things that people have in the past or even in the present used as filters to try to safely view an eclipse. And none of these objects on this list are safe to use to look at an eclipse. And that includes sunglasses, especially solar filters. These is an old style, and I think they're actually illegal now, and they're certainly not sold anymore. They're also called sun filters. I remember getting one of these with my very first telescope many, many years ago. And those filters screwed into a telescope's eyepiece. And then you would put the eyepiece in the telescope and let the telescope focus all sorts of solar radiation on that, on concentrated solar radiation on that filter. Those filters were known to crack under the heat. And even that brief glimpse of light that comes through after it cracks was enough to damage people's eyesight. So these are no longer available. And if you find one somewhere, like, destroy it, get rid of it. Also, photographic neutral density filters. These are not safe for solar viewing with your eyes. Polarizing filters, same deal. Any kind of photographic film that's been exposed and looks pretty black, again, it's not safe because the blackness is not uniform. So you might get some areas of the film that is darker than others and you think might be safe, and then you move it a little bit and you get into a lighter part, and again you run into troubles. Okay, so any kind of color or black and white negative film, forget it. This is just get rid of it. You're not going to use that. People have also used smoked glass, believe it or not, just glass with a layer of soot from a candle flame to blacken it out. This is really dangerous because it doesn't take much to wipe soot off that glass there and leave you with an unfiltered area. So again, forget that. Aluminized polyester food packaging. And it's a new one I'd heard of it, but I can see where people would use it, kind of like the Mylar blankets that you see. They do cut a lot of the sunlight, but again, they're not created to uniformly filter out all the different rays of sunlight, I believe, that would come through them. So you're not only worried about visual wavelengths, the ones that we can see, but you're also worried about infrared transmission and ultraviolet light transmission. None of those things are healthy for your eyes, so forget those. CDs, yeah, you don't want to look through those. Also floppy disks, if you take the old 3.5-inch disks and take them apart, you'll see a very dense medium inside there. But again, not suitable for this purpose at all. The bottom line here is don't take any chances with your eyesight. I mean, the eclipse is a marvelous thing to see, but it's certainly not worth trading any part of your eyesight for. You need that for all your days. All right, next one, please. So how can we photograph the eclipse? I've shown you ways to look at the eclipse, making a projector as well if you don't have any other equipment. I know a lot of us are interested in photographing the eclipse. And for those that have been in the game for a while there, we tend to use something, as you can see on the left-hand side here. And that's a camera and a lens on a tripod with a glass solar filter, or one of the bad enough filters as well there. But I tend to use the glass solar filters there. Just it's preference, and I actually kind of like the orangey light that it transmits. But it's individual preference. But the beta films, the light that you'll see or capture is more whitish light there. So it's a matter of preference, really. A lot of cell phone photography going on these days. People doing more and more astrophotography with their cell phones. And if you've got a pair of solar eclipse glasses, those are more than suitable for putting in front of your telescope or your cell phone lens there, acting as a solar filter, and you can try to try your hand at taking a solar image. But again, you don't want to expose the lens of whatever camera you're using, either a cell phone or any other camera. You don't want to expose that to raw sunlight for really any kind of period of time, other than maybe a fraction of a second. Even then, you're kind of taking your chances, because sunlight is very, very potent. And if you're doing like the girl's doing here with her solar eclipse glasses there, and she leaves, if that wanders off the lens there for a few seconds, it might destroy the camera, might destroy the camera sensor. So it takes your chances there, but this is a way that I know that people have been using their cell phones for imaging. Next one, please. As I mentioned here, this is another image actually that Andrea supplied me. This is going to be her setup for photographing the eclipse, where she's done a solar filter using the Bader solar film and mounted that onto the front of her lens. So camera's mounted on a tripod. She's got a good solar filter ready to go. And I'm crossing my fingers and hoping that we all get that sunlight, Andrea. The other one that is very common for folks that have been in the game for a little while is a glass solar filter mounted in the front of your telescope. These tend to get a bit more expensive, obviously, because they're larger in size. But if you want to have a close look at the sun during this eclipse, you'll need a telescope. Even a relatively large telephoto lens will show you the whole disk of the sun without really getting up close and personal to it. On the other hand, your telescope will let you zoom right in. Especially interesting if there are sunspots on the disk, and you can watch the moon either uncover sunspots or cover them up, depending on where they are. This particular image shows a glass filter mounted at the front of the telescope, and this gentleman has done some extra security and mounted Velcro straps on the front of that filter and attached to the telescope to make sure that filter does not come off. So again, if you're doing photography or visual observing through your telescope, the last thing you want, even for a second, is for that filter to pop off. And again, a reminder that if you have a finder scope on your telescope, if you don't have a filter for that, keep that thing capped, especially when you're using a telescope for visual observations, or you might find the top of your head getting uncomfortably warm if that finder scope is focusing rays of sunlight on your noggin. So you want to kind of avoid that. All right, next one, please. So I won't explain too much about these because if you've got one of these, you already undoubtedly know how to use it either for visual or photographic observations. But these are choice instruments too for viewing solar eclipses. The scope that you see on the left-hand side is a dedicated solar scope. It's a Coronado personal solar telescope, a small 400 millimeter unit, and it is only for observing the sun. It blocks basically all the sunlight except for the hydrogen alpha wavelengths there. So you can actually see detail on the surface disk of the sun using one of these telescopes, which is really kind of cool. The other object that you see on the right-hand side is called a Herschel Prism, or also known as a Herschel wedge. You can use these you basically use them with refractors, not reflectors, but with refractors, and you can use them either visually or for photographic use, but you have to also use them in conjunction with the appropriate filters, neutral density filters for your particular scope and application. And so if you've got one of these, you also got instructions on recommendations for the use of the particular neutral density filter that is required for these. But these are nice items to observe an eclipse with as well. But they come at a price. These tend to be pricier items there, and so probably not a lot of those out in the field. All right, next one, please. So just a few tips for you for those that are interested in actually photographing or trying to photograph the event. Oh, hang on a second, a bit of a glitch on my end here. There we go. Oops. Sorry, I'm still glitching here a little bit. Okay, so if you do want to try to take a picture, mount your camera on a tripod to get a steady image so you're not shaking it around, especially if you're using a telephoto lens. You saw the two configurations using the glass and the Bader solar filters. Before you do anything else, ensure that your solar filter is firmly attached to the front of your lens. I can't stress this enough. You don't want it to be, loosey-goosey or something like that, where you could accidentally nudge it off or even have the wind blow it off. I noticed Andrea had a bit of a shield around hers that extended beyond the barrel of the lens there. That is for trying to shield some of the sun from hitting the camera and stuff. but that could also make a bit of a sail in a higher wind. And so you want to make sure that, again, nothing's going to take that filter off your lens. Use a remote or a wired shutter release or an intervalometer to get steady exposure, so you're not clicking the button with your fingers. Use the camera's live view LCD screen for framing and focusing the view. Okay, you don't want to look through the viewfinder, even though it's safe if you've got a good filter on the front of your lens there. But the live view makes it easier, and you can actually zoom in with the live view on the edge of the sun to do your focusing. So it gives you a bit of more precise focus. You've got to turn your autofocus off because it's kind of it may be kind of useless there. It just depends on how bright your image of the sun will be. Okay, you also want to set your camera to be in manual mode so that you can control the exposure settings, such as the aperture and the ISO and the actual exposure length. So yeah, turn off the autofocus, turn off the auto ISO, and you don't need a high speed for this type of photography. Set it to a low value. That gives you a much cleaner, less noisy image. Set it down to around 100 or 200, and then you can adjust your exposure accordingly. Also, you might want to stop your lens down by a stop or two, just to use the sharpest part of your lens to get the sharpest edges on the disk of the sun. So I'm going to give you like a few seconds here. I'm just going to button up, and I want you to read that last paragraph in white, please, at this point in time. Okay, so basically, just a word of advice here in terms of trying to grab these pictures. If you've never done eclipse photography before, it gets pretty exciting when the eclipse happens. And with this eclipse starting at sunrise and really not lasting for that long afterwards, you're not going to have time to practice framing and focusing and trying to determine your appropriate exposure. The eclipse will be over before you know it. So you really want to try to practice this stuff beforehand. In the next few days, when it looks like we're going to have some nice sunny days there. Practice beforehand so that you're used to doing this, and if you do go out and try to grab this on Thursday morning, that you'll already know what you need to do. You can have it all set up, and you'll be good to go. So you can try to do photography with a wide-angle lens. You will only get a very small image of the sun that way. But you won't have to probably move your camera at all. If you use a telephoto lens because you want a larger image, you'll have to probably reposition that as the event goes on, unless of course your lens and camera are piggybacking on top of a telescope that's that's being driven by a mount. All right, next one, please, Chris. So the last couple of words I have for you here on this subject. And I've already been asked about this actually by a couple of people, is if you want to create a view like this, how do you go about doing it? Well, a view like this, you cannot capture in one go. Okay, there's just way too much dynamic range on that sun. Even the shortest sun exposures are going to reveal a pretty bright sun, even with just a sliver like that viewing, and your foreground will be dark. So for those of you that took the astrophotography workshop, you know where I'm going with this. You can do a composite. In other words, you take an image of the sun, your filtered image of the sun, and get a nice definition on the crescents there, and then you superimpose that on a regular image of your foreground that you can take. Say after the eclipse is over and after the sun moves out of the field of view, just take a normal picture of the scene at normal exposures, and then with the magic of GIMP or Photoshop, you can then superimpose them and get an eclipse view of that landscape for your scrapbook, for your memories. All right, last couple I'm going to show you. So again, to stress the point, this is a shot that I took at the eclipse in the total eclipse in Wyoming back in 2017. And what this is hang on a second, I'm glitching here again. What this is an unfiltered view of the sun. So I was taking pictures of the sun with my solar filter on, and I know I'm probably going against a little bit of what I've been warning you about. I did not look through or anything. Obviously, I wasn't going to be that silly, but I did uncap my camera lens for a fraction of a second. I already knew what exposure I wanted. I set that exposure. I uncapped it for a second and banged off a 1/30th of a second shot and quickly recapped it. This is right after the end of totality. This is not the full sun. This is right after the end of totality, and you can see that the image is still pretty blown out. Like that sun is pretty bright there. So the last image I've got for you here is a filtered view that I took 3 seconds later with the filter on, and you can see that brightness that you saw in the previous image was caused by that tiny thin sliver of sunlight poking through. So this is the filtered image 3 seconds later. So all this is just to go to show you that do not underestimate the sun. Do not look at any part of this eclipse with the unaided eye, and make sure your filters are in good shape, and just be very, very cautious with it, especially with the low sun angles we're dealing with. It's going to try to fool you. Don't let it. Okay, clear skies, everybody. We're going to cross our fingers and hope we get some good views of this. Thank you.
Okay, thank you very much, Paul. There was one question there I just answered online regarding the cell phone. She was worried about her glasses falling off, and I said just bring some Scotch tape and tape them to the phone. So I think that's probably the best thing. I use electrical tape myself to hold my covering on the end of my telescope because it's not a really tight one, and I'm always worried about it blowing away.
Yeah, I do the same thing. I use Velcro straps, and even though I've got a snug focus here, it's just, yeah, it doesn't take long for disaster to strike.
Yeah. Okay, just a second here. I'm just going to rename myself back, and I can't seem to rename myself for whatever reason. Hang on a second. Oh, there we are. I was hidden behind. Okay, folks, we're going to move on to our observation reports here. So first up is Bob Olson, and the spotlight you. There you go, Bob. You're on.
Okay. How do you do? This is M85. It's one of the challenge objects this month. And, you might be asking which one it is. Next image, please. And there you go. And M85 is interacting gravitationally with that galaxy below. Next image, please. This is a pretty edge-on galaxy. It was also a challenge object. It's quite close to M85, so I didn't have to move my telescope much. It has a very interesting dust lane and is commonly called the Needle Galaxy. Next image. The last non-lunar challenge object was Leo 1, and I spent almost 2 hours imaging it before I realized that it looked astonishingly familiar. Next image. It was the challenge object last year, and except it was identified by its UGC number of 5470. You might ask why it took me 2 hours to figure this out, but I'm old and I have difficulty remembering what I had for lunch yesterday. For me, the interesting part about this image actually is that M11.2 galaxy is 9,000 times dimmer than the magnitude 1.3 Regulus. And you can still get a picture of them both. It shows you how well modern cameras and telescopes operate. And you might ask where I got that 9,000 times dimmer thing. It's a fairly simple logarithmic relationship you can figure out, but I cheated and used Google. Just put the numbers in. Next image, please. M4 is pretty globular cluster, very easy to find in binoculars or a small telescope, as it's very close to Antares, which is a bright star low in the southern sky. Next image, please. M23 is an open cluster that you can find above the tea kettle in Sagittarius, low in the southern sky. You can see the red from the light, the fact there's diffraction from the atmosphere. It's low in the sky. Next image. This is M22, and it's just above the tea kettle of Sagittarius. Its magnitude of 5.5 make it the brightest globular cluster that's visible in Canada. And this caught me off guard, as I thought M13 had that honor. Next image, please. M20 or the Trifid, is one of my favorite astronomical targets, and I've imaged it several times before. You might ask, why image something more than once? I guess I'm always hoping the image will be better than the last time. But in fact, it's just like seeing an old friend. To use your children as an analogy, you don't take one picture of your kid and then put your camera away. I think the plague is ending soon, and I wish you all well. Thank you very much.
Okay, thank you, Bob. I'm going to turn over to Richard Taylor.
Okay, I always seem to follow Bob Olson, and my equipment is nowhere near as powerful. So you're going to see some of the same objects through a much smaller telescope. This is the William Optics Z73. So here's M85. And because of the COVID restrictions, I was kind of restricted for most of the time to my own driveway here in Ottawa. So there was a lot of light pollution. I was using some very short exposures, about 10-second exposures at ISO 1600 on the camera. But I did manage to find it. So here's I found it picture of M85. Next one, please. Now, this one I thought was a much more exciting object. This is the Needle Galaxy, but I also found it has another name. It's Berenice's hair clip, because it's right up near the Coma Berenices, the cluster of stars, which I actually prefer the name of the lion's tail, because it is really just above the end of the Leo constellation. So that was the intermediate challenge, and I did manage to get out to some darker skies for that. My brother let me use his driveway down near Athens, Ontario. So it was a lovely evening last Saturday, and I managed to get some pictures of this one. But I combined it with the ones I got from my driveway here in Ottawa, and that enabled me to get a lot more of the detail in that dust lane. Next one. Now, I'm not using any kind of go-to telescope. I just aim at using a red dot finder. So I have a lot of star hopping to do, which I really enjoy doing that. So this is actually on my route to finding M85 and the Needle Galaxy. I aimed at Denebola, the tail star in Leo, and then moved about halfway to Vindemiatrix in Virgo, both of which were visible from my Ottawa driveway. And aiming at that portion of the sky, usually I could find M99, which is the lower left galaxy in this picture. And if I turned the camera just right, within the same field of view, I could get M100, also known as the blow dryer galaxy in the upper right corner. And I thought this pair of galaxies and all the other little galaxies in between made a much nicer picture than M85. So maybe that's a hint for some future challenge object. Next one, please. And here's the lunar challenge, crater Landsberg. And it turns out to be very close to last month's lunar challenge, which was Reinhold crater. And both of them are very close to Copernicus. So you've got this line of three, Copernicus, Reinhold, and Landsberg, all of which have double or multiple rims. So there's quite an interesting sequence of craters there. But Landsberg, like Copernicus, has a very nice and interesting central peak to it. So that was May 22nd, which was the closest I could get to having those on the Terminator. And then the next night, next picture, I also got Landsberg, but since it was farther from the Terminator, you can't see the rim in as much detail. But I was very happy to see that I got Tycho showing both some detail of its rim, its central peak, and also the rays as well. I was quite happy with this picture. I posted it on the RASC Facebook page and got a lot of interest on that. And some people were asking, do any of these rays coming from Tycho have particular names? And I'm afraid I've never heard of anything like that. So if anybody knows of any particular name for their individual rays coming from Tycho, maybe you could look on that Facebook page and answer the question there. Okay, thank you. That's all for me.
Thank you, Richard. I'm going to turn it over to Oscar.
Hey, everyone. So this is Messier 64, which is also known as the Black Eye Galaxy. The Black Eye, which is that sort of dark region you see near the core, is thought to be some very intense star-forming regions in the galaxy. This galaxy is notable for being composed of two counter-rotating disks. So there's an outer disk and an inner disk, both of which are rotating in opposite directions. All of the stars in the galaxy, though, rotate in the same direction as the inner disk itself. So the fact that these two disks rotating in opposite directions, there's a zone where the two disks rub, and it's then that rubbing is thought to be the cause of the intense star formation in the inner ring. This image was taken using an SBIG STC7 camera that I picked up last November. I haven't done any imaging through it until now, though, using LRGB filters through a Celestron Edge HD11. So it's an LRGB composite with about 35 minute subframes of luminance and 15 subframes for each of the color filters, for a total of about 6¼ hours of data, all the processing done in PixInsight. So yeah, it's my first kick with that camera. I hope to do a little bit more work with it and improve my processing there of composite images. Thank you.
Okay, thank you, Oscar. I'm going to turn it over to John Thompson.
Oh, okay. I was expecting the Mercury image as the first image. Okay, well, this one, you may have heard on March 19th, a Japanese amateur astronomer discovered a nova, which hasn't really made as much press as I thought it would, because it's the first one since 2013 that became a naked eye object. It just barely, it reached 5th magnitude about 3 weeks ago, but it was discovered at magnitude 9.5, went up to 7, and it stayed at 7 for about 4 or 5 weeks. And then it bumped up again to magnitude 5.2, and then it dropped to 7. But since then, over the past 3 weeks, it's been gradually brightening again. And this is very unusual behavior for a classical nova. Normally, they go to a peak and then make a gradual dimming over the next 6, 8, 10 weeks. But this one, after 10 weeks, it's still brightening. If you want to find it, it's an easy binocular object. That star 4 Cass, you can find it by taking the two right-hand stars of Cassiopeia, which are 5 degrees apart, and moving upwards for another 6 degrees, and you'll hit that 5th magnitude, star 4 Cassiopeia. And then the nova is about 1.5 degrees south of 4, or it's about half a degree south of M52, if you want to look at it that way. There's a couple of interesting comparison stars. That HD star is magnitude 6.6. In this picture, that was at its peak on May 12th. Since then, that was at magnitude 5.2. Since then, it's dimmed to 7, but it's come back to, or 7.5, sorry, but it's come back to about 7.1. So it's still ongoing, and I think this one will cause some interest for the astrophysicists because it has a rather unusual behavior. Now, the next image is the same field taken with a Prism spectrograph. Now, it's not the same one that I wrote about in Astronauts a couple of years ago. It's an improved version, and I'm still working on improving it. But you can see normal spectra are a band of colors, sometimes with dark discrete lines, which are absorption lines from various elements. This one has a very bright emission line, which is hydrogen alpha. And then further up, you see a bright line of hydrogen beta. And there are actually further lines, hydrogen delta and gamma. And if you do an analysis on it, you actually find other elements. I've done an analysis which will be presented probably in another meeting, but it's been interesting following this. And that 4CAS also is an interesting spectrum, that rather than lines, it has bands because it's a cool enough star that molecules of titanium oxide are able to form. And rather than having a discrete line, you have a band absorption. Next slide. Oh, was the one of the Mercury, Mercury a pulse? Mercury.
We only had 2 in for this time, John.
Oh, okay, because it was also on May 28th, Mercury and Venus came into conjunction, and they were only 0.4 degrees apart, and I had that. I thought that was being presented. Okay.
Sorry, John. We'll get them in for next month. Okay. Okay. So next person up is Paul Clark. So hang on, Paul. Let me just spotlight you. There you go.
Oh, good evening, everyone. This is my first time up presenting anything, and this was a shot I took on May 18th. I was going out to my observatory just to roll off the roof to acclimatize for the evening, and I saw the moon. And I had bought a piece of equipment that apparently attaches your phone to your eyepiece. So I thought the moon was so prominent, I thought I'd try it. I took 5 or 6 shots, and this was one of them. And I merely showed it to Rick Scholes about this, and he said you should present this. And I really wasn't going to. Then all this discussion on our listservs were going about whether one should use phones or this or that. And my comment about this is that depending upon the tool, it might be useful for different things. And so this shot was taken with a phone. It was one of 4 or 5 that I took. It was a little difficult framing. I guess you'll note that I cut off the top point of the crescent. And that was just taken with the typical phone software. My next 2 shots, I came back 4 days later, and I tried doing the phone again using a specific app that permitted me to access the raw files and adjust things like exposure, sensitivity, the EV value, all that. And I took these shots, this shot and the following shot, merely to illustrate it can be done. So there you go.
Thank you very much. So we'll turn it over to Andrea. There we go.
Hi. So my images, the next 2 images were taken with a new monochrome camera, and astronomers like to use monochrome cameras because they're more sensitive than color cameras. So this is my first adventure using a hydrogen filter. This is NGC 7000, the North America Nebula, and we are looking at the Gulf of Mexico. And the same image, next slide, please, Chris, this is the same image, but a different sort of area that I zoom in on, and that is the Pelican Nebula, which is right next to it. So these images were taken through a hydrogen filter. And I also then, a couple nights later, took more images through an oxygen filter. I don't have a sulfur filter yet, so I can only combine them now to the palette, which is known as HOO. So I assigned the hydrogen to red, I assigned oxygen to blue, and I also, green, I did a combination of the hydrogen and the oxygen. And in the next image, you'll see what it looks like. And so this is what they call a false color palette, a narrowband palette. It's a little softer than I would like, but essentially that's what happens when you assign just the hydrogen and oxygen to different colors. I was quite pleased. It was my first time doing narrowband imaging, and there was lots of detail on the camera. I think the black and white cameras really do collect a lot more data. And I think I had about 3 hours of imaging with hydrogen and 3 hours of oxygen. Okay, next. And I've also decided to try and do some Milky Way photography, which is quite different from the deep space stuff. And actually, I think it's much more difficult. This was taken not far from my home, and that is part of the problem. With the Milky Way, you really have to get to a dark site. And I was surprised because I thought this site was very dark, but the camera picked up an awful lot of the city light pollution, and I had to sort of fix it a bit with Photoshop. But this is a tracked image. So I did get a star tracker out. I had a regular Nikon camera. I had a 10mm lens, which is very wide angle. And I just pointed it south and I tracked for 2 minutes. And this is a stack of about 5 2-minute exposures. And it turned out not too bad for not far from home. And next image. I then decided to point the camera up. And I was, it's a lot less light polluting the sky that's straight above you. And this turned out to be quite dramatic. It's actually only 2 exposures of 2 minutes. And you can see the dark dust lanes, really dark lanes of the Milky Way. And there actually is a little bit of red. And that reddish part is the Cygnus region around the Satyr star and the North American Nebula. So it's a different viewpoint. Again, it's a tracked image, 10mm lens, and you can still see actually at the bottom a little bit of the city light pollution. So as soon as we're allowed to leave home, I'm going to have to go and find darker skies. So those are my images. Thank you.
Okay, thank you, Andrew. I'm going to turn it over to Paul Klauninger. Are you going to turn on your video, Paul?
No, I'll leave that off.
Okay, so I'm just going to spotlight myself, and I'll just turn off my face. Okay. Okay, go for it.
All right, thank you. So this is Astro. This is an artist's conception of an interesting object that's buzzing around our solar system called asteroid Apophis. This was discovered just actually relatively recently, back in 2004, and it has an orbital period of about 324 days. The thing that makes this asteroid interesting is it's a good size. It's about 370 meters or 400 meters in length. So, we're looking at a rock about the size of the Empire State Building. It's small, and it caused a lot of alarm actually back after its initial discovery, because early computations of its orbit showed that it was going to come fairly close to Earth, and in fact, for a while, it was raising a lot of eyebrows and getting right up there on the scale of hazardous objects you don't want near your planet. And in fact, what's happened here, especially this year, is that it did make a close approach, a relatively close approach to Earth, but not one to fear. But I'll tell you about its next approach here in just a second. Bottom line with this asteroid, given its size, let's say roughly 400 meters or so, it's traveling at about 31 kilometers a second. And asteroids like this are calculated to impact the Earth about once every 80,000 years. Okay, so it's not a frequent event, but certainly in astronomical time spans, it is relatively frequent. You just don't want it happening when you're around or if you're anywhere near it, because it's estimated that if this asteroid impacted on the Earth, it would release the equivalent of about 1,200 megatons of energy. Contrast that with the largest thermonuclear bomb that mankind has ever torched off. That was 50 megatons. So this is substantially bigger. And in fact, the small asteroids or cometary bodies that formed the Tunguska impact in Russia back in the early part of the 20th century, and also the Barringer crater down in the States some tens of thousands of years ago, those were estimated to release somewhere between 3 and 10 megatons of energy when they impacted. So Apophis has the ability, if it ever did impact on the Earth, to create a crater probably about 5 kilometers across, and it would basically devastate thousands of square kilometers around its impact site. Compared also with the eruption of the volcano Krakatoa in the East Indies back in the latter part of the 19th century, that volcano blew its top and caused measurable changes in the Earth's climate for a couple of years after its eruption. And it was estimated to release the equivalent of about 200 megatons of energy. So we're talking about a pretty serious event here. So back in March, next one there, please, Chris. I did take some images of this thing just because I'm curious about it. And what you see here, this is actually a composite of 5 images, and I'll get you to throw the next one up there, Chris, which really just shows the direction of motion here. Those 5 dots, that is asteroid Apophis. These are 30-second exposures taken about 5 minutes apart. So you can see its motion over the span of about 20 minutes here. Took this with the 11-inch Edge HD and the 60 DA camera. This asteroid is interesting because this was a reasonably, it wasn't a close approach to our planet. It was still several million kilometers away back in March. But the next approach was a worrisome one when they did their initial calculations. Well, I'll show you this next image there, Chris, just to give you an idea of what we're looking at. The original image I showed you was an artist's conception, but this is the real thing. These are radar images obtained with the Arecibo dish when back in 2012, and you can see the asteroid was tumbling and stuff. You can see various faces of it. So this is a pretty solid object there. And the next slide shows you what they got worried about when they started refining its orbit. On April the 13th in 2029, this is going to come extremely close to our planet. In fact, it's going to come closer than the geosynchronous satellite belt. And when it does its closest approach, it'll move across 42 degrees of sky in an hour, and you'll be able to see this with the naked eye if you're in the right place. Unfortunately, it's not North America. You'll have to be in Europe, I believe, to see this. Good excuse for an astronomical vacation. But it's going to be about magnitude 3, so it should be pretty easily visible in a reasonably dark sky. And you'll see it move across, as I say, 42 degrees in an hour is pretty substantial. But it's the close approach that is really interesting. As I say, it'll be closer than the geosynchronous satellites there. And this was what had people worried. But with subsequent observations of this object, we could relax a little bit, because the more observations we took, we were able to refine its orbit and realize that it wasn't going to be a threat in 2029, that it would be a near miss, but just barely a near miss. And again, follow-on observations for other dates that were worrying us in 2036 and in 2068 have also now been ruled out as potential dates for an impact of this asteroid on the Earth. The one to worry about, and I guess we won't have to worry about this too much, is in about 100 years from now, 2116. The uncertainty in its orbit, obviously, in a century is a lot more than this with the next nearest passes here. And it's going, again, to come uncomfortably close to the Earth. And the interesting thing is with these asteroids that they obviously, with close approaches like this in 2029, their orbits get changed. And because they're irregular in shape, they can be subject to uneven amounts of thermal heating from the sun and even ablation of some of their surface materials. So this is one of the reasons that their orbits start to get uncertainty the longer out that you look. So you're going to keep a close eye on this puppy for 2116, and hopefully we'll avoid a collision with it. And in a century from now, if it looks like we're going to collide, hopefully we'll have the technology to go out and give it a whack out into the outer regions of the solar system. So that is asteroid Apophis. My last image there, Chris. This is just a little bit of a follow-on to the Moon series that Jim and I were working on in the early part of the year. This image I just took 3 weeks ago. And you can see that it was at the right phase and such. And you can see that the lunar mountains, the south polar lunar mountains that we've been talking about, are somewhat visible, not as prominent as they were earlier in the year. And that goes along the lines of Jim's excellent simulations. And it's related to the fact that the lunar librations for the next number of months, when the moon is in this phase, are not favorable to showing these mountains. And so essentially, they'll kind of disappear from view and will reappear again once the librations become favorable, probably starting in October and November. So that's it for me this month. I wish you all clear skies and stay safe.
Okay, thank you very much, Paul. So moving on to observation challenges. Last month, we had Messier 85, NGC 4565, Leo 1, and Crater Landsberg. Glad to see that some of you are able to show us some of those. Let's move on to the ones for this month. So our beginner challenge is Messier 84. It's a lenticular galaxy in Virgo, 55 million light years away, 10th magnitude. And so these will all be posted in Astronotes. So I know these slides are moving quickly, but we will put all these in Astronotes. Next one. Intermediate challenge is NGC 5689. It's a lenticular galaxy in Boots, 11.9 magnitude, 120 million light years away. Next one. The advanced challenge is the Abell Galaxy Cluster 2065. It's in Corona Borealis, 1.2 billion light years away. And that's for the advanced challenge for this month. And then moving on to our lunar challenge, the impact crater Lasus Salmonarium. I'm not sure I pronounced that correctly. 2.3 kilometers deep, 95 kilometers in diameter. And there's 13 total craterlets, half the alphabet. There we go. So see if you can, how many of those you can capture on your images. Oh, okay, moving on. So this is a summary of our challenges for this month. And next slide. So right now, with the current Ontario restrictions, a limit of 5 persons to the Fred Lossing Observatory are on site and 1 person in the observatory. So to coordinate this, please send an email out to the group before you head out there so we don't have too many people on site. Hopefully in the next number of weeks, we'll be allowed to have more people there. So here are the folks that keep the club running, some of them. So Rick Scholes is our flow director. We do have a STEM book library. It's inside of the closed Aviation and Space Museum. And once we get that reopened, Estelle will be busy with that. Okay, moving on to the next one. We had 93 tonight. Thank you to all the organizers and speakers. Thank you to the RASC National Office for use of their Zoom account. Any comments or ideas, please send them to myself, meetingchair@ottawa.rasc.ca. I've got a bunch of speakers lined up for the next number of months. Thank you to those who have responded. Right now, I have openings in November and December for speakers. Apart from that, we've got pretty well a full slate of speakers up until then. Okay, if you'd like to become a member at the RASC, I would encourage you to do that. Regular membership is $88. Family membership is $82.50 plus $15 per adult, $8.10 per youth. And we have a youth membership for $53. So for this membership, local benefits that you get is the Ted Bean Telescope Loan Library, the Stanmont Library once the museum reopens, and access to the Fred Lossing Observatory out near Almont. And then from the national office, you get Sky News, comes out every 2 months. That's our national magazine. And then we also have the Journal, which you receive electronically, but you do have the option for an extra cost of getting that in hard copy. We have the Amazing Astronomer's Handbook that comes out in around December each year. And we have our locally produced Astronauts that comes out every month, thanks to Gordon Webster, our editor. Our next meeting is Friday, July the 9th. We're not having it on the 2nd. It's too close to Canada Day. Many people are taking that day off. It's a long weekend. So join us July the 9th, 7:30 p.m. At that meeting, I've got two speakers from the Montreal area of the RASC. One of them is talking about ancient astronomical instruments, and the other one's very keen on space shuttles and rockets. I don't have the exact title of their talks yet, but it's going to be an interesting evening. So thank you very much, folks, for coming out tonight. Stay safe. And some of us will be up early Thursday morning. Hopefully we have clear skies for the solar eclipse. So thank you for coming, folks, and have a good evening.